Do we have the slides? Yes, no. Thanks a lot for the great intro. So this talk today is about V8 internal, so join the secret V8 club and become a JavaScript bender. And if you're not sure what V8 is, you are in the right talk because that will be the first part. Before that, I'm Vlad. Everyone calls me Vlad. My pronouns are he, him. I'm a staff engineer at Datadog. I'm part of the Node.js community as a collaborator. I've authored the async local storage APIs. Those are very nerdy Node.js stuff. But if you're into JavaScript security, I wrote a course on Coursera that is very accessible. Feel free to follow me on Twitter if you want the slides and if you want to yell at me because you don't like my talks, or to congratulate me if you like my talks. So what is V8? V8 is a JavaScript engine. So the legitimate question is, what is a JavaScript engine? And a JavaScript engine is a program that takes JavaScript code as inputs and executes it. And it can compile or interpret that JavaScript code. It's not really important. It just executes it. And there are multiple JavaScript engines on the market. V8 is one of them. You've got SpiderMonkey, developed by Mozilla, or you've got JavaScript Core for the Safari that everyone loves. And V8 is the one developed by Google, originally for Chromium and Google Chrome. But it's also the JavaScript engine used by Node.js, Deno, MiniRacer, and many more. So when you are using these tools and you run JavaScript, basically you have V8 under the hood running this JavaScript code. V8 is an open source project. You can find the source online, and there is a mirror for GitHub. It's mostly written in C++. And if you want to learn a lot of things about V8, I recommend following the v8.dev blog by the V8 team. So, as I told you, V8 executes JavaScript. So if I give that as an input, we've got a for loop with number from 0 to 10, and we console.log. And we will call V8 directly on the right-hand side. We won't use Node or Chrome. We could do this. We could call this code in Node, Chrome, Deno, or anything, but here we use V8 directly, and without surprise, it prints numbers from 0 to 9. Yeah. Now, what happens if I want to run this chunk of code, document get element by ID, directly in V8? Does anyone know? What?
A name error?
Yes, exactly. It crashes because document is not defined as part of the ECMAScript specification. It's part of other specifications that are proper to web browsers, but not the JavaScript language. And here's the thing, V8 just runs JavaScript, but you need to provide a context with new APIs when you want to interact with something outside of your JavaScript program. So let's say you are in Chromium. Chromium bundles V8, Chrome bundles V8, and provides APIs that can be called in JavaScript to interact with the DOM. And same thing for Node. Node basically embeds V8 and provides APIs for the JavaScript code to interact with the operating system and the network. And if you have ever written Ruby, you might like this project. It's called MiniRacer, and basically enables you to embed V8 in any Ruby code base. So you can build your own clone of Node or Deno or any server-side runtime, but having JavaScript code calling Ruby code that you have defined. And that's actually very straightforward. And Deno actually embeds V8 and provides a Deno object, and then use another engine. So V8 does not only just interpret JavaScript. So what happens when you provide JavaScript code to V8? Well, first of all, it will parse it and define what's called an AST, abstract syntax tree. So that's basically a set of objects that represent the code as passed. And when the code is passed, it will go in a first subengine named Ignition. As you can see, there's a lot of name coming from the car industry. But that's because it's an engine, I guess. And Ignition basically generates bytecode and executes it. So it's really fast to generate the bytecode from your JavaScript code, but bytecode is slow to execute because it's interpreted. Then you've got Sparkplug. Sparkplug will generate machine code from your JavaScript code very fast, but this code won't be optimized. And then you've got a slower engine, slower in the sense that it is slower to generate code, but provides code that is already optimized. So it's called turbofan. And right now the question in everyone's mind is, what the hell is optimizing code? And thank you for asking this question. So there are multiple ways of optimizing functions. Two of the main are inlining functions, so you don't have to jump in memory to call the function, and compile the function when it has a stable signature, when the types of the input and the outputs are stable. So let's take an example with the myAddition function, which takes A and B as arguments and returns A plus B. And since we are JavaScript developer, we know that A and B can have all the types in the world. And let's take this function and call it 1 million times with integers. So we've got a loop, and we call myAddition with I and y plus 1, and this I and I just go from 0 to 1 million. And I push it in an array. It has nothing to do with the benchmark. It's just to prevent V8 from optimizing, because it knows that myAddition is a pure function, and if the output is not used, V8 is smart enough to remove the function call because it does not have any incidents. And we'll start this code with V8, and as you can see on line 1 on the second chunk, we have -- trace opt, which means trace optimization. And we put a grep at the end of the command line, so we see only the thing related to myAddition. So on line 2, here we've got marking myAddition for optimization. Reason, it's a small function. That means that V8 is detecting that this function can be optimized, so it will push it to turbofan and start optimizing it. Then we have a log saying, hey, it's actually compiling, a log telling it's optimizing, and a log telling us, hey, that's done, you can use this function. And now the optimized code path is used. And it's easy to optimize because this function is small and has a stable signature. And since I am extremely sadistic with V8, I will torture it and force it to de-optimize the function. And it's actually very easy to do because you just need to change the type of the inputs, and that will change the signature, and V8 does not like that, and we like to push V8 in situation it doesn't like, do we? So on line 10, we have the same chunk of code, but instead of calling with integer, we call with integer strings. That's still valid JavaScript, right? Because type don't matter and nothing matters in life. Sorry, that was dark. So we take our logs on the right-hand side, and we have the same log from line 2 to 5, but on line 6, we've got bailout, de-optimizing reason, not a SMI. And what is a SMI? A SMI is a small integer. It doesn't have anything to do with big integers, just now for now that there are two kinds of numbers in V8, things that are called number, small integers and big and other integers. And we'll go to them later. But here, yes, the signature of the function has changed. It has gone from small integer, returning small integer, to small integer, string of small integer, returns string of small integer. So V8 has to not use the optimized function anymore because it's invalid. It has not the proper signature, but it can still re-optimize it. So here we have the same log. Hey, you know what? I can optimize it with a new signature. I re-optimize it, and I use that. We could be even worse and put other type later to torture V8. You know what? That's what we're gonna do. So meet get, oh, my new favorite function. That was the name of my first pet. So it takes item as an input and returns the property O on item. And once again, we'll call it 1 million times with an object. And this object is defined as I being the integer that is incremented, and A0, a stable property that never changes. And no surprise, V8 is happy to optimize it, as we have seen that. Yes. And now, because we are mean, we call the function with A0OI. You know, it's technically the same object in JavaScript, right? Wrong. Because on line 6, we have the optimization reason wrong map. What does that mean? That seems extremely weird, especially since per the JavaScript specification, those two objects should be equivalent. Well, every object in V8 has what's called a hidden map, and that's how it's implemented. So because objects have just a very wide type that is object, V8 can't optimize for object. So it defines a hidden class for each object you create, and if two objects are created the same way, they can have the same hidden class. And that's the type V8 will use for optimizations of functions that use objects. And we even have a method in V8 that enables us to check if two objects have the same hidden class. So if I take the object A0O10 and A0O11, they have the same hidden map because they have been created with the same properties, who have the same type in the same order. And if I check the object A0O10 and O10A0, they won't have the same map because they have not the same property created in the same order. And that's this kind of very deep V8 stuff that can sometimes solve your life. And I see like people are frowning about this percent in front of my functions, so let's talk about the native syntaxes and the percent function. So if I call console.log %max SMI, told you we will come back to SMIs, then it crashes and it tells me unexpected symbol %, because it's not actually a valid JavaScript symbol for a function name. But we can call V8 with a flag that is hello native syntax that will enable using these native syntaxes. And now we can see the value for max SMI. I'm not trying to read that in English, not even in French, but just know that it is not a constant. It depends on the version of V8, but also your operating system and hardware, because it actually depends on the addressing space on the memory. Small tip, you can set V8 flag from within Node.js when Node.js run. For Chrome, you need to put the flags when you start the process. Just make sure that you don't pass code before the flag is set, otherwise it will crash with this error can't unexpected token. Are the native syntax documented? Of course they are not, because they are internal of V8 that are mostly used for testing and debugging. And basically, if you want the list of them, you can find them in the V8 source. And if you want the documentation, you can grab the V8 test and find them. And sometimes some of them are very useful. For instance, most recently in the Node.js codebase, we had a test that would not work if a function got optimized. So we use the native syntax that prevents function from being optimized altogether. And these functions, this native syntax, can help us answer the deepest question of mankind, or maybe JavaScript. First question, are optimized functions really faster? That's a legitimate question. Do you have to care about your code being optimizable? Well, let's take add O, which is a slight variation of get O that takes O on the first argument and adds the second argument on that. And on the first version of this function, we'll call never optimize function, meaning we're telling V8, this function, you don't optimize. Then we have exactly the same function. We put a warm-up, so it has type information. We force optimization of the optimized one with optimize function on next call. Yes, they are not documented, but their name is actually pretty simple. And then we just have making sure that the optimization happens and has time to happen. And we use benchmark.js because it's still the best benchmark suite for me. And we start the benchmark. And what we see is that the non-optimized track can run up to 70 million operations per second. But the optimized track runs even twice as fast, 161 million operations per second. So yeah, optimization do matter. Can I check the optimization status of function from within the code? Yes, you can even know how it is being executed, whether it's interpreted or used through the baseline compiler. So here we've got a getO function, the same one as before, and we will call it with variable objects, so just OI, OIA1, B, hello. We are just putting weird types and weirder different maps. But after each call, we call a function named print status if changed. Source code will be on the next slide. And we can check the logs. So here, the function, when we start with simple objects, it is interpreted because we did not have time to put it in Sparkplug, yes. Then on the line 6, we've got K baseline, meaning, hey, it has been going through Sparkplug, and we have the fast compilation that happened, but it's not optimization. Then we've got optimization state of the function. It's being optimized in another thread. And eventually, we've got the optimized version of the function that is called. Then we changed the signature of the function by calling it with the other object, and V8 starts by crying and say, you know what, I can re-optimize that. So we go back to the baseline compiled versions because it doesn't have type assumption in it, and then we have another updated one. And we can do that again and again. Just know that at some point, V8 will give up on your code. After a function is optimized, de-optimized, re-optimized, re-optimized, V8 will give up on your code and stop optimizing. If you want to check the optimization status, you can use this function. I don't want to go in depth about that because they are bitwise operator and they are scary for me. But I just stole that from the V8 source code for the test. Basically, I just cached the status because the status is a number. You put it in binary and you use bitwise operators to know which elements of your bytes are 1 or 0s. And you've got the list of possible states on the left-hand side. So we are very early than what I thought on the talk. Sorry if I spoke too fast. But that's good, I guess, because I won't be over time. Can I manipulate memory-related stuff? Yes, you can with native syntax. Please don't do that. Yes, but I still want to dig into CPU and memory stuff. Yeah, we can observe it. Rather than interact with it, we can observe it. Which in quantum physics means the same thing, but we're in programming, so let's not care about this part. So who loves the DevTools? Ah, yes, they're amazing. One of the first things I do when I have to mentor a younger engineer is, let's learn how to use a debugger, because print is not a best way to debug stuff. Because debuggers are so powerful, you can check the state of the memory. But ever wondered how it worked under the hood? In the browser, in Node.js, or in other runtimes? Well, let's take a look at that. Enter the Chrome debug protocol. Chrome debug protocol is basically a protocol you can execute over WebSocket to a V8 target, or to a browser that implements it as a target. So you can call the debugger programmatically, the heap profiler, the CPU profiler, code coverage data, DOM APIs, DOM debugger, all of them are accessible through the debug protocol. And even like the Playwright library that enables you to automate web browsers is actually using that to control Chromium, because they just open a WebSocket and connect to it and use the debugger. And if you want to remote debug Node.js or Deno, that's how you would do. And that's actually extremely powerful because it gives you access to everything in a running process. So on the left-hand side, I know it's a bit small, but we use the inspector node modules that gives you access directly to the Chrome debug protocol from within Node. And we call profiler.enable because we enable the profiler API on the target process. And then we call profiler.start. We do some code, and we call profiler.stop. And that will return us a JSON file that actually contains the CPU profiling output, the one that you can see in the DevTools. But yes, and if you want to see something in detail, you can always script it. If you want to find a function in particular, sum its calls, know how it's called, who calls it, and stuff. And there's something that's available in the debug protocol that is set sampling interval. And to explain what it is, I have to explain quickly how does the CPU profiler works in V8. Basically, it works by polling. It checks every n milliseconds what is the current function running and what is the call stack for this function. And it will just say, hey, so this function is running, this has been running from then to then because I have seen them in that many consequence tick. But sometimes you have functions that are smaller and that are called in a loop. And V8 will just show you one single call because the sampling interval is actually too big and has statistically bad calls on your function. And you can actually change it, but you can't change it from the UI, but you can change it from the protocol. It will come with slowdown in your code. But if you need to know, you need to know. You also have access to the heap profiler. And the heap profiler is extremely powerful because it gives you access to everything in the heap of your JavaScript process. You can get a heap dump. So here are example of API call where I just say heap profiler that take heap dump. And you can check them and dig into the heap dump inside the DevTools. And it's extremely powerful because you will see all objects, all strings that are currently alive in your process heap. So if you have a memory leak, that's probably one of the first things you want to do. Funnily enough, the objects in this view are sorted by their class, not their hidden class, the class you defined as a programmer. So when you are fighting memory leak and you are just building objects with literals, you will hate what you have done in building objects because you won't be able to find them by class and find where they are from. So it's usually a good practice if you're afraid your application is data intensive and there is pressure on the garbage collector to use classes even if you don't think they will bring a lot to your code. You will thank yourself when you have a memory leak. But Vlad, most of that is available in the dev tools. What's the point? Yeah, I know, but sometimes you need to remote debug. Whether it's a Node.js process running in a cloud infrastructure, or you want to do automated diagnostics. You want to parse a heap file and make sure that you don't have the same memory leak you used to have in the past because you already debugged it and you want to have non-regression. And script debugging is actually very powerful and has been around computing for a lot of time. But we are running out of time, and you can check my previous talk at Node Tel Aviv about if you can change the behavior of a process, of a Node.js process from the outside. I wish I would be able to talk about other topics, but they are all talks in themselves, so it's more like opening doors. You can check V8 inline codes. It's actually very brilliant, and you can write a lot of huge articles about that. Also, V8 treats WebAssembly. There is a fourth engine in V8 that is dedicated to WebAssembly named Litoff. That is another brilliant piece of technology. Yeah, I know. Last time I gave this talk, someone tweeted, even people who build V8 don't love V8 as much Vlad does. Guilty. V8 manage strings, because remember, I told you we've got hidden classes for numbers like small integers and other. Well, guess what? Strings too. And depending on how you create the string, it will be internalized in memory, it will be defragmented in memory. So even the topic of strings in V8 is a topic by itself. The Turckheim language is amazing. It's like a language designed by the V8 team to implement the ECMAScript specification in V8. So it's a language that will compile directly to V8 bytecode, pre-optimized, and that's how they write the spec. Feel free to go to the source, and that's pretty cool. And last but not least, V8 snapshots. They are coming to Node, they are coming to a lot of places, and they enable you to start a process directly in a certain state. So just to help the bingo, just async faster. And if you're interested more on that on v8.dev, thanks so much for your attention. You've been an amazing crowd.